All right, we have found ourselves at section 15.8. So, for those of you who are my students here at Western Illinois University, and you've been following along now for 3 semesters, this is it. This is the last section in the textbook. It's taken us 3 semesters, but we have finished the entire textbook. So, before we jump into 15.8, let's take a look at where we've been so far in chapter 15. If we go back several sections to 15.4, we introduced Green's theorem. And what that theorem did is it allowed us to compute line integrals over simple closed curves via double integration. Then in the previous section, 15.7, we introduced the divergence theorem. And what that theorem allowed us to do was to compute the flux of a vector field across the surface instead of via a surface integral, instead as a triple integral using the divergence of the vector field. 15.8 is focusing on Stokes' theorem, and that theorem allows us to instead compute line integrals over simple closed curves as surface integrals using the curl of the vector field. So before we get into Stokes' theorem, let's first talk about positive versus negative direction. So we have a definition here that says, let sigma be an oriented surface bounded by a simple closed parametric curve C. Suppose a person is walking along C with their head in the direction of orientation of sigma. The person is walking in the positive direction of C relative to the orientation of sigma if the surface is on the person's left, and the person is walking in the negative direction of C relative to the orientation of sigma if the surface is on the person's right. So I think that this picture here, which you can see is taken from the textbook, there's a citation figure 15.8.1, is really illustrative of what we mean by positive and negative direction. You can see this piece of the surface sigma, and you can see its orientation is pointing upward. So we have our normals pointing upward. That means that we want the head of the person to be pointing upward as well. So you can see that in parts B and C. In part B, this person is walking along the surface, and you can see that to her left is that surface. So that would be a positive direction. There we go. And in part C, the person is walking the other direction, and now the surface is to her right. That would be considered the negative direction. All right, so we're going to keep in mind positive versus negative direction of a curve C. We also have a remark here reminding us of how to compute the curl of a vector field. Given a vector field f with component functions lowercase f, g, and h, the curl is given by the determinant of the matrix whose rows are first the I, j, k unit vectors, second the partial derivatives in each coordinate, and third the component functions. Oftentimes we write this as the del operator crossed f. And so I just want to remind you here that the curl operator inputs a vector field and outputs a vector expression. So the divergence of a vector field outputs a scalar expression. The curl of a vector field outputs a vector expression. So we can now talk about Stokes' theorem. It says, let sigma be a piecewise smooth oriented surface bounded by a simple closed piecewise smooth curve C with positive orientation. If the components of the vector field are continuous and have continuous first order partial derivatives on some open set containing our surface sigma, then the line integral over the simple smooth curve, piecewise smooth curve C of f dot dr can be expressed instead as the surface integral of the curl dotted with n ds. So we need to remember how to compute surface integrals throughout this section. All right, so let's take a look at our first example, use Stokes' theorem to evaluate that line integral. So before we do anything, we see our vector field F. Let's go ahead and compute the curl, and then we'll talk about the orientation. All right, so what is the curl of this vector field? So I'll fill in my I, J, and K across the top, my partials across the middle. and then the component functions across the bottom. All right, and then let's carry out the determinant here. I'm going to strike through the first column. And when I look across the first diagonal, I see 0 for the first partial. And then the second diagonal is going to give me a -1. So 0 minus a -1, and that's for the I hat component. I always negate the J hat component, so strike through. I get a -1 minus 0. And that is J hat. And then finally for the K hat, I'll strike through that column. I get 0 minus a -1. 0 minus a -1, and that is the K hat component. And so my curl here is 1, 1, 1. All right, so now let's read through the rest of this problem. C is the circle, x squared plus y squared equals a squared, in the xy plane with counterclockwise orientation, looking down the positive z-axis. All right, so first of all, we see that we have a simple smooth curve. Namely, it is a circle of radius a. And so I'll indicate the radius here on the x and y axis. And furthermore, it says when you're looking down the positive z-axis, then you have counterclockwise orientation. So that's specifically how we're looking at it, right? We have a bird's eye view looking down at the xy axis. And so I indicated here that we have counterclockwise orientation. If we want to be going around this curve in a positive direction, then what we want is we want our head in the direction of the surface orientation so that the surface is to our left. So we want to be walking in this counterclockwise direction, which means our normals need to be pointing upward. All right, so I'm just going to make a note here, counterclockwise orientation on our curve C means upward normals. So when we're talking about computing this surface integral of curl of f dot n, what could we use for n? Well, we just want to be going upward in the z direction. So that's just k hat or 0, 0, 1. So in this particular example, our normal was easy to compute because our surface lied only in the xy plane. And so a normal was either in the positive z or negative z direction. And we chose positive based on the orientation of our curve. All right, so let's go ahead and apply Stokes' theorem. It says that the, line integral over c of f dot dr is going to be the surface integral of the curl 1, 1, 1 dotted with the normal 0, 0, 1. And we're changing that surface integral into a double integral where our region here is this circle. All right, so we have our basic setup. Now we're recognizing that since our region is a circle, we likely want to use polar coordinates. So let's set those up. Theta is going to run from 0 to 2 pi. The radius is going to run from 0 to a. And when I carry out my dot product, I get 0 plus 0 plus 1. And then dA becomes r dr d theta. All right, so then let's carry out this integration. First, I'm going to integrate with respect to r. That's going to give me a 1/2 r squared, where r is ranging from 0 to a d theta. So that is the integral from 0 to 2 pi of 1/2 a squared d theta, which is a 1/2 a squared theta, where theta is running from 0 to 2 pi. The 2 can cancel with the 1/2, and we're left with a pi a squared. All right, so the value of the line integral over the simple closed curve C of f dot dr is pi a squared units. Now, in this example, it was fairly easy to pick off a normal because, again, our surface was lying in the xy plane. It was not slant at all, so the normal was very easy to compute. If that normal n is not obvious, you can use one of the two following facts depending on your setup. So we're going to assume that our surface is of the form z as a function of x and y. And then depending on whether it's oriented upward, so here I'll use a different highlighter. If we're oriented upward, we're going to use negative del z del x in the I hat, negative del z del y in the j hat, and then a positive 1 in the k hat. Here where it's understood that this is del z, we just don't write it. Now, if we're oriented down, then we're just going to use the negative of that normal from part 1. So you're just going to want to look at which part of this remark applies to you based on your situation here in working out these problems. So let's look at our last example, number 8, use Stokes theorem to evaluate the integral over C of f dot dr. Here again, we have our vector field. Before we even get too deep, let's go ahead and compute the curl of this vector field. So I have I, j, k across the top, partials across the middle, and then the component functions across the bottom. So let's compute this curl. I'm going to strike through the I column. And when I look across the main diagonal, that partial with respect to y is 0, minus the partial with respect to z is 4. So what I get here is 0 minus 4 I hat. Now we always negate the j hat term. So I get 6 minus 0 here. 6 minus 0 j hat. And lastly, strike through the k hat column. I get 0 minus a negative 6y. 0 minus a negative 6y k hat. And so my curl is negative 4, negative 6, and positive 6y. All right, now let's take a look at what our surface is. It says C is the triangle in the plane z equals 1/2 y with the given vertices with counterclockwise orientation looking down the positive z-axis. So here we can see that our surface does not lie in a coordinate plane. It's on the slant plane, z equals 1/2 y. And we have our vertices. But what's important here is that we have a counterclockwise orientation. And that's when looking down the positive z-axis. And so that tells us that we're going to want to use an upward direction when we think back to our remark. So let's scroll back up here. All right. So we are oriented up since it's counterclockwise. Again, very similar to our last example where we wanted our heads to be upward so that when we walked around our circle, the surface would be to our left. So same thing here. This means we're going to be using remark number 1, and we want to use this yellow vector here for our normal. So I want the negative partial z partial x and the negative partial z partial y, and then a positive 1 at the end. So let's go ahead and set this up here. So the line integral of f dot dr is instead going to be, we'll come back to our limits of integration. I'm going to set up my curl, which is a negative 4, negative 6, 6y. And then I want to dot with negative partial z partial x. All right, so let's highlight. This is the equation we're looking at up here. You'll notice that there is no x term. So that partial is going to be 0. Then I want the negative partial of z with respect to y. So that's going to give me a negative 1/2. And then finally, I get partial z, which is just 1 dA. So if I carry out this dot product, I get the double integral over r of 0 plus 3 plus 6y dA. All right, so now we need only compute the limits of integration here based on what our curve is. Now we know that C is a triangle and a plane. And remember, we had vertices in 3 space. And those vertices were 2, 0, 0, 0, 2, 1, and 0, 0, 0. We want to project these down to the XY plane because Z was given as a function of X and Y. So our region R is the projection in the XY plane. So basically what we want to do is we just want to drop off those Z coordinates and we get 2, 0, 0, 2, and 0, 0. So let's sketch that in the XY plane. All right, and here is our region. So at this point, we need to decide, does it make sense to integrate in rectangular or polar coordinates? Here, we definitely want to use rectangular because this is not a polar region. And so what I'm going to do is I'm going to come up with an equation for the hypotenuse of the triangle. Here we have a y-intercept of 2, and we have a slope of -1. So y equals 2 minus x. This bottom equation is, of course, y equals 0. And so I'm going to take vertical slices. So our x is running from 0 to 2. Our y is running from 0 to 2 minus x. And we have our integrand 3 plus 6y. And because I took vertical slices, that's going to be a dy dx. All right, and so now it's off to the races. We can go ahead and integrate first with respect to y. That's going to give me a 3y plus a 3y squared, where y is running from 0 to 2 minus x. Of course, plugging in 0 is going to drop everything out. And so what I get here is, I'm going to go ahead and distribute the 3 here for this first term. This is going to be a 6 minus 3x. And then I have plus 3 times 2 minus x squared. So that's 4 minus 4x plus x squared. And all of this is going to be integrated with respect to x. So let's go ahead and simplify here. I have a 6 and a 12 gives me an 18. Then I have a -3 and a -12 gives me a -15x. And then I just have a positive 3x squared. All right, and we integrate with respect to x, 18x minus 15 over 2x squared plus x cubed from 0 to 2. We won't plug in 0. And so what I get is 36 minus 30 plus 8. So 6 plus 8 is 14 units. All right, this concludes our final section of this textbook, 15.8 Stokes Theorem. Thanks for tuning in.